I have no idea what to do. The first step, beyond understanding that you have a law of motion and that you can integrate it and look at local stability, is to start developing qualitative theory of all possible motions in dynamical systems. This brilliant idea comes from Henri Poincaré more than a century ago, who understood that it was more important to think about celestial mechanics in this case. It was more important to think about qualitatively what differential equations can do rather than try to get analytic solutions for particular cases, which was fashion until his time. Mathematics and physics got divorced with the invention of quantum mechanics, so this was not pursued by physicists for almost 80 years or so, but it was pursued by an extremely able group of Russian mathematicians, in particular Kolmogorov and his students Sinai and Arnold. And in this story today, Sinai is the important student. And they started developing a modern intuition, which I'll try to explain, about qualitative behavior of dynamical systems. So the idea is you have a dynamical system, meaning you have a state space and law of motion. There is a dynamical system. What the law of motion says, if you start here, you go someplace. I'm drawing Poincaré sections from now on. And you emerge here. So at the time t1, or just call it x1, meaning the discrete time, you're here, and then sometime later you reappear in your Poincaré section at time x2 and so on. So that's what you know so far. Poincaré says, well, this is too much information at the moment. Could we sort of divide this into 3 regions? And you just tell me what happens if I start in a region, where do I go? The example that's very intuitive and that we already know very well is the 3-disk example, which I'll use a lot. So here is how qualitative dynamics works for 3 disks in a plane. You start someplace on disk 1. Qualitatively, what can happen is you can either end up on a disk 2, or you can end up on the disk 3, or you can escape through the gaps between the disks, and we won't care about you. If you do that, you'll be gone from the game. So very coarsely, what's going on in this dynamical system, I have very precise information. I have position and the angle of every trajectory as it hits a disk. But qualitatively, I either end up on 2 or 3. So you can imagine that you make your dynamical system state space divide in 3 regions. I'll ignore again the holes. This gives you some information about the kinds of solutions. What happens next is very typical for unstable systems, so systems that have some hyperbolic structure. And that is, you can ask yourself, can I do this a little bit finer? Let me try to categorize possible behaviors, but what happens in 2 time steps? So for example, what can happen is that if I start here, I'm guaranteed in this pencil of initial conditions, I'm guaranteed to come back. But if I go someplace over there, in this way, I'm guaranteed to go to the 3rd disk. But if I start in gaps in between, I run away. And the obvious thing from playing pinball game, you know, is that trying to hit the sequence of bounces is much harder than hitting just one, because you have to be much more precise about initial conditions. In other words, in the chaotic or unstable dynamics, it's the dynamics itself, meaning the history of what has happened, that helps us classify the motions. So what that will mean in this case is that each one of these regions, which is here, meaning the perimeter and parallel momentum or angle on each disk of 3 disks, these are these 3 regions. If I insist going 2 steps in time, I'll find that these regions get subdivided into smaller regions, where the first region has a property that I start in A and stay in A, the next one I start in A, I go to B, I start in A, I go to C, and the same thing will happen to these coarse regions. So in statistical mechanics, what I'm doing is called coarse graining. You are not specifying initial conditions infinitely precisely, but you find you go from C and then you end up here, or you started in C and you ended up in B, or started in C and end up in C. And here you start in B, end up in A, you start in B, end up in B, or start in B, end up in C. So if you have a system that's unstable, then its history starts giving you a more and more refined partition of the state space. So I want to tell you this is totally different than running computers, because what people tend to do when running computers is they take the dynamical system, so they take our Poincaré section, which is some curved 10 or 100 or 1,000 coordinates, whatever dimension dynamical system is. And then what they do is they just define it, divide it in little hypercubes, because computers like hypercubes. And then they study whether you visit the hypercube or not. Now, you know, that's stupid, but that's what people do. Dynamics actually is much kinder to you. Dynamics itself teaches you how to partition the state space. You don't have to put rectilinear coordinate systems, because dynamics will do this. And as we go further and further in time, each of these regions will get subdivided. And if a system is nice and hyperbolic and you have taken care of all the continuous symmetries that I ask you to take care of, etc., this will end up at infinite level of resolution. There will be only one point specified by each symbol sequence. These things are called symbol, and sequences are called itineraries. You know, what you visit in a given time. That's the main strategy of understanding how to classify possible motions. Just let dynamics teach you how to do it. Don't force it yourself. That's what I want to do for a little while, and it's a very powerful idea. It was, as far as I know, you know, maybe it goes back to beginning of 19th century, but in this functional way that I'm describing now, as far as I know, it goes back to Sinai. The reason why this is very important to theoretical physics in general is that this connected deterministic ergodic systems and statistical mechanics. Once you start thinking this way, suddenly lots of ideas that are very natural, like Ising models, etc., or Ising models in statistical mechanics, they fertilize your thinking ergodic systems, and vice versa. It's very important the other way around. You know, this is the way of starting to think about far from equilibrium statistical mechanics, which is the great outstanding problem of modern statistical physics. You know, what do we do with systems which are not in equilibrium but in some kind of steady state? Turbulence is a good example, and many other examples. This is a great idea, and I will try to formalize it a little bit and explain it, and I will also try to tell you that this is actually extremely difficult idea. Ergodic theory is much more difficult than quantum mechanics, even though we find quantum mechanics so magical. And the reason will be that in deterministic ergodic theory, the rules of what itineraries are allowed or not are very difficult to determine. So that's